Hello, hello, hello. I'm Marco. Thanks for having me. It's the third time, I think, already for me speaking here at the Insomniac, and I must say it's quite nice conference. So I really like coming back here. It feels like family. You know me, I know you, every one of you. And like in the last years, I know we're in the French part. I'm sorry, I don't speak French at all. I guess most of you don't speak German because I'm from Germany, so we talk in English. That's okay, hopefully. And then let's start. I guess Operation Triangulation is already quite a term some of you, most of you are kind of familiar with. And I thought it's such a complex but very, very interesting operation we investigated and uncovered. And I want to share with you really interesting details about all of that. First, to me, I mean, for the ones who just know me by face or whatever, or not at all, I'm part of GREAT. That's the Global Research and Analysis team. Our main aim is research. So we dig into APTs, targeted attacks, everything what I usually say, the fun stuff, where you really go deep into the things to uncover what's really behind all of that. And then today, yes, it's on purpose that it's blurred. At the end of the presentation, you will have the clear picture and you will understand. So it's just like, this will be our path. So the interesting thing, first of all, Operation Triangulation, it's a targeted attack against iOS devices. That's, of course, bummer number one. I mean, iOS, it's a black box, as most of you know. It's not that easy. You cannot simply go like with your computer and install whatever kind of software. It's locked down. You have very, very limited abilities to really control these devices, just the stuff what is allowed. So having these kind of attack against iOS is quite outstanding by itself already. And the fun stuff is that we also detected at our own company with our own employees. And due to the complexity, I think it's fair to say that this is the most sophisticated thing we discovered so far. Let's see what's come next, but so far, that's the thing. I'm not a big fan of doing agenda slides, honestly, so I'm sorry for that, but for this, just for you to make it easier to follow, we go through 4 main steps. First, how we discovered it. Then we go through the attacks chain, which is more like the exploit side of things. And then we have a look at the malware and then a brief conclusion. So if you're lost somewhere in between, you know, oh, there is something different coming, which is maybe more of interest for me or whatever. So bear with me. We dig through many different interesting aspects. So discovery. As I said, iOS is a black box. So you cannot simply go and install an AV or sensor or whatever kind of stuff. So what we basically, how it made it possible for us to discover it was because of several mistakes of the attackers. That's most cases like the thing, that the attackers do some mistakes. We've seen it in many, many different operations we uncovered over the many years. And the good thing for us is they just need to do one mistake. It's like with the police. The criminals just need to do one mistake and you catch them. And having an operation running for many, many years, in most of these cases, what we look into, the percentage of likelihood increases over time, usually, that some mistakes are made or technology changes and the adoption is not ready in place. So black box device, no chance. So we need to look at the network activity. And the network activity was quite interesting because we have, of course, network monitoring, and some of our employees' iOS devices, iPhones, made some weird connections. And at first sight, I mean, backuprabbit.com doesn't look super suspicious. It's not one of these low-level criminal random generated domains you initially see, okay, that's something fishy. It looks more decent and okay-ish. But of course, we do some more checks than just having a look at the domain itself. The interesting thing here is, you will see it in the next slide, they always come in pairs. All of these domains are behind Cloudflare and Namecheap. Why though? Namecheap enables that you don't see who registers it, and Cloudflare for second layer protection of the original origin. So what we saw from these iPhones was simple. First, you had a call to the official Apple server for an iMessage attachment. That's okay. That's totally fine. That's how things are going. Because in this attack, we're talking about something which comes through iMessage. By default enabled. Who has an iPhone? And who disabled iMessage? 1, 2, 3, or? Okay. I should raise my hand as well. Okay, so there is some attachment through iMessage. Interesting. And after that, you initially have connections to 2 of the domains. As I said, they're always in pairs. It's not 1, it's always 2. So that's kind of weird. So we went into checking what's behind that. One thing, what you can do on iPhones is you can do backups. And if you know it, then you protect your backup with a password. You can set this in the settings on your computer, iTunes, whatever, macOS. And only if you set a password, it really backs up everything from the iPhone. If you don't set a password, it doesn't. So we did backups to see, hey, what are these connections? But the attackers are quite intelligent from that perspective, that they try to clean everything what's happening. So, of course, they clean the initial attachment from the iMessage. But the folder itself where it's stored is left over. So you have an empty folder for an attachment which is not there. That's already kind of suspicious, because why would there be an empty folder without any content? iMessage does not randomly create empty folders. That's not the purpose of that system. And on iOS, maybe I should explain this because we have this later on as well. Basically, every information on an iPhone is stored in a database. It's usually an SQLite database. And for every different app, you have an SQLite database. So the attackers went on and cleaned from the SMS, DB, and some others, all of the information tracing back to the initial exploit and attack. But they forgot about the data usage database. So that's an internal iPhone tracking database to know which app uses what data and so on and so on. So we have a second clue. And then that was kind of the final thing. In iOS, it's quite an old system, right? So it's there for many, many years already. And since kind of the beginning, there is this app called Backup Agent, which is not used anymore. It's outdated, but it's still in the firmware. And out of a sudden, this app started to become active and also generate network activity. So even if this app usually is active, it doesn't communicate on the network level, which means, okay, we have an application which is usually inactive and also does network activity. That's not cool. The good thing for us, that's the technology side of things. They didn't implement any kind of man-in-the-middle detection. So because we cannot go on the device, we needed to operate on the network level. And on the network level, due to the not implemented man-in-the-middle detection, we did exactly that, man-in-the-middle. So man-in-the-middle proxy routed all the iPhones through our proxy in order to intercept all of the traffic, what's happening. Finally, we were able to do it, of course. That's also the output of this presentation. But what we did is, what we found basically was many different stages and layers throughout this operation. So we had device fingerprinting stuff, which I'll discuss later. And we have different stages and everything, and that's the tricky part, is encrypted with 2 levels, AES and RSA. So you cannot simply on the fly crack AES and RSA, right? I mean, we know that. So what we did is basically we live patched from the different stages the communication keys in order to decrypt the traffic and step through all of the steps of the exploits, malware, yada, in order to get all of the information run through this attack. It was very intense. The scripts added to man-in-the-middle proxy were like thousands of lines long in the end, because all of the different things what we needed to change on the fly in order to get to the final data. But we got everything. So let's dig into what we got. The attack chain itself, it includes a huge amount of zero-day exploits. Interesting is it's not just one, it's many. That's already quite a lead to the point of how funded this operation was, probably. First, I said it's an iMessage. So an iMessage account sends an iPhone an iMessage. The thing here is it's a 0-click. You don't see it, you don't smell it, you don't notice that there was an iMessage coming. Because in that iMessage is a PDF, and in that PDF is a TrueType font exploit. And already this does everything. You don't notice it. It's 0-click, no interaction needed. You have iMessage enabled, you get this iMessage, done. Game over. That simple. Sorry. So TrueType. TrueType, it's a super old font format developed by Apple, of course, back in 1991. Was ported to Windows 3.1 already. On the Windows platform, many exploits were, vulnerabilities were detected in that and patched. That's at the background. So this exploit was written also in TrueType VM assembly language, and it referenced to undocumented instruction. Interesting. Undocumented instructions are usually always something when you're hunting, like, okay, there's something odd going on. So the colleague who digged into that was checking everywhere, like, what do these functions do? Nothing, except one super old source code from Windows where it just says, okay, that's an Apple-only instruction. Yay. Okay, so we have an exclusive Apple instruction. One function which is undocumented and probably there since the beginning. Where might this exploit be? I'm not sure. So basically the exploit itself, it's, I don't do these animations usually. So it's basically just he developed a mistake because he copied some code which enabled remote code execution. That simple. Which is bad, was reported and then patched by Apple, first in iOS and macOS. Yes, it's basically the same core platform. I hope you're all aware of that. All the Apple operation systems in the core basically are the same and just derived from the cores. So you have a similar type of kernel, the XNU kernel. I reference that later on. And just on the top layer, there are different implementations. So it was patched in January 2023. By that time, it was already being abused by the attackers. And later on in July, also patched for older versions. But there since the 90s. Yay. Then, that was exploit 1. If you want to dig deeper in the exploits, we can discuss, but I think it's not interesting enough to dig through all single instructions there. Because we have more to talk about. So, point authentication code. On common systems, you usually have some authentication, some protection for pointers. On ARM, they're using, like on Apple, Pakitsa, which is pointer authentication code for instruction addresses, and the set here can also stand at the end. Means just that the modifier is 0. Technical details, yay. Basically, they're used in order to sign and check pointers that you cannot simply go wild on a system. But the attackers know about that, of course, and they abused two weaknesses here. Too many pointers are assigned, and they're all found in memory, basically. So what they did, it's a very simple thing. They went through certain functions, got designs, built some fake headers, and finally got to the point that they were able to sign any pointer whatsoever. So done. That's a simple, not so simple, bit complex, but it's an okay-ish authentication code bypass. That's needed in order to execute further. So we have the true type with the CVE and the PAC bypass. Then they were doing a lot of return and jump oriented programming stuff with NS expression. NS expression, if you don't know it, it's a language on Apple devices. It looks simple, but it's super powerful to do many, many, many different things. And the attackers used it in order to change the Java core to prepare it for the next steps of the exploit. Basically that. And then changing a lot to the kernel exploit. Because that kernel exploit, it's written in the JavaScript. And for that, they changed a lot of things on the Java engine. And that's quite interesting one. First, they enable the debug feature of $VM, which is important for read-write instructions. And there is no just-in-time compilation happening. So they're just going through patching it and then creating a huge JavaScript file with the exploit. After deobfuscation and reformatting, it's about 11,000 lines of code. So that's a JavaScript kernel exploit on iOS. 11,000. It's huge. Okay, so what it does. A lot of this code are callbacks to call direct API functions out of JavaScript. So basically, they're just handlers. So with that, they can basically do everything what they want on that system, which is quite interesting. Then they added another exploit, a simple integer overflow in the XNU, the kernel of Apple, overflow in that kernel to do stuff. And another one that's, I guess, the most interesting one, because that's hardware based. And you know, when you can abuse hardware for your exploit, that's also game over, because the problem with hardware is you cannot patch it. Problem. It's not so cool. So there is a hardware feature on this things where you can just write to any address, data, whatever kind you want, because it uses an unknown MMIO, memory mapped input-output registers in the firmware. So they're not used. They're there. They're super powerful. Brief explanation. So Apple chips are so-called SoCs, system on a chip. That means that things, what you usually know from your computers, you have like your main board and your CPU and your graphics card and yada, yada, yada. All of that stuff is implemented into one chip. Therefore, system on a chip. So you have the CPU, the GPU, you have all of the I/O interfaces, GPIO, I2C, and so on. And the CPU works with memory mapped I/O, what I just said, MMIO registers, in order to address all of that. And we found that the exploit uses some certain addresses which we didn't know about. You cannot find them in device trees for the different firmwares. We checked source code, kernel images, everything. 0. It's also an M1 desktop system. You know, we're just talking about iOS usually, but it's also in that system. Many of the exploits are. So that's quite interesting. So we have calls to certain MMIO registers, addresses, but we don't know what it is. That's weird. Not documented. Again, not documented. Over time, we found out, okay, it's somewhere in the graphics buffer registers. So the GFX stuff, that's for graphic buffers, and then there are 2 blocks basically used by the exploit. It's in between somewhere where you have like the GPU halt and enable, disable stuff, which is like the usual hardware stuff, and then you have like the low addresses and stuff like that. The interesting thing here is that, it's not clear how did the attackers got to know the MMIOs, because they're not documented. I mean, if you have a documentation, okay, but not documented. For us, still, even though we got some more information later on, after we first published about that exploit, because it uses some kind of ECC algorithm, which is usually used for memory stuff. So it seems it's a direct like cache interface to cache in a very complex way. Like the implementation, you really need to know the algorithms the key tables and stuff like that, for an undocumented hardware feature, again. And it's not clear if it was just some Apple thing or for ARM or whatever, because Apple is using ARM nowadays. Luckily for us, Apple patched it. No one shouts at me. I said we're talking about an exploit with hardware, which you cannot patch. And I just said Apple patched it. Come on. Come on, wake up. So basically, they just put in their firmware for the addresses they're abused, they deny in the device tree. Yay. Okay, so they mitigated it somehow. Still unclear to date what that really is. Maybe a debug interface or whatever. Very likely it's a debug interface, but who knows? Direct memory access through the hardware to everything. Just to escalate it again. So we have the $VM enablement, the PAC bypass we've shown before, the two different CVEs, the integer overflow in the kernel and the hardware thing. That's the kernel exploit. After that, it goes further. Of course, it always does a cleaning. They are very careful about being silent and under the radar and stealth. So they always do this cleaning. And then it goes to a validator. That's quite a common thing. First of all, you would say like, yeah, of course, the attackers want to know who they are attacking, if it's really the target they want to get into. In this case, it's a bit more complicated because first we have this JavaScript validator. And this JavaScript validator does a lot of different things, specifically also one, which it uses canvas to draw a yellow triangle on a pink background. That's also why we dubbed this operation triangulation. It calculates the hash of that and uses that to send it back to the C2, probably as some kind of unique device identification. It's a common method usually also in the advertisement area. Canvas fingerprinting, quite known. They also implemented it. Among that, they also collect a lot of other information. Wait, come on. Yeah. Then there is another Java exploit, a Safari exploit. I think we mentioned it before, or not. It's just a common one. Going to a kernel exploit binary this time, with the same CVEs, but not implemented in JavaScript, but in binary, to another validator. And that's the interesting point. So we don't have only a targeted list where this iMessage is sent to, so they already know where they're sending it to. It's not mass spreading. Going through a whole list of exploitation to get to a first validator, another chain of exploiting to a second validator. And that's quite outstanding because that's usually a case when you have very, very, very limited and specific set of victims you want to address to. Because as you would do it already, like in the first validator, right? That's like the usual case when you have a validator, you do it there. And the second one is a binary validator, so not JavaScript. Binary always means Mach-O, that's the binary format. Like on Windows you have exe, on Linux system it's ELF, on macOS it's Mach-O. And it runs a lot of different operations, deleting logs again, jailbreak detection, and it also has some unused actions. So it detects and tries to identify if there's some traces from any kind of like this backup agent, what I mentioned before. That was the app which is usually not active and was active. So they try to delete everything from these activities, from the WebKit, from the iMessage exploit chain, always trying to clean as much as possible through all of these stages in order to be as clean as possible. This also tries to clean the senders of the iMessages. And that's the interesting point. So the iMessage was sent from what we now know based on this binary validator from 40 different Apple accounts. So iMessage only works on Apple. You need an Apple account, and there's specifically one. And this binary validator implement all of these 40 in MD5 format, which is not super crazy to crack, honestly. So we run through, we identified all of these 40 hashes to get the original Apple IDs out. We reported it back to Apple so they know about to lock them down. That's an interesting sneak peek of that. A lot of jailbreak detection, what I just said. So all the famous ones, they also try to identify if Corellium is running, so if it's a real iOS device or just an emulated one. A lot of different... Come on. He says I need to hurry up. And also PSP Detect, which is quite interesting because on iOS there is no personal security product, so maybe it referenced to something else. It sends a lot of information back, including also the advertisement ID, because it's a validator, right? So if that's past everything, it goes to the malware. So let's quickly go through the malware. That's super interesting. Because first of all, it's developed in Objective-C, so it's a binary. It is of course modular as many. It uses for communication HTTPS, again, encryption, and protobuf. Protobuf is a method for serializing data. Just think about JSON, but more efficient, kind of. It's more efficient. It's not really JSON, but just as a reference. So the code probably is already there more than 10 years. That's pretty clear based on all of the things which is implemented. So it gives you a trace of how long this operation was either planned or already conducted. Again, as I said, two C2 servers. All the messages are with triple DES and RSA, encryption, yay, as a post request. And the one we checked implemented 24 different commands to do basically everything what you can imagine. Like everything what you as user cannot do, this piece of malware can do. It can directly interact with the file system, with the processes, and it can dump a lot of interesting information what they're after. Just a few things because that's really important. Keychain exfiltration. Keychain on iOS is where all of your passwords are stored, your certificates are stored. So all of the sensitive information is in Keychain. What they're basically doing is they wait till you unlock your iPhone. Because then it's accessible, they dump all of this information and they have it. If it's locked, they cannot dump it because it's encrypted. That's the trick. Interestingly, it's directly implemented in the malware, but there is also an additional module basically replicating the same method, which is kind of interesting because, yeah, maybe different development teams, more developers who didn't know about. And it supports different keychain versions starting from iOS 4. It's quite some time already. We're at what? iOS 1 bazillion, something like that. They have a module for microphone recording. It usually is only active when the battery is over 10%. so it doesn't suck the battery empty. That's good. They implemented their own custom format to store all of the information in chunks. It's again compressed and encrypted with AES, sent back to the attackers. Location module. Usually you have GPS, right? Okay, but what if GPS is not available? They have a fallback mechanism to also use GSM. So they got all of the GSM-based data from the cell towers. That's 2-3 meters, something like that, 2 meters, 3 meters, correct on your location, which is interesting because who uses GSM for that? They do. And they have many modules to steal and parse and extract SQLite databases because, as I said in the beginning, everything is stored in SQLite. So you have everything photo-related, WhatsApp, SMS, Telegram, and all of the different versions, because throughout the versions of iOS, also formats of the SQLite databases change. So they have from like below 8, then between 8 and 9, and then starting from 9 and up. That's basically the three main different variants of your SQLite databases, which is all implemented, they can take care of. So the version doesn't really matter. Photos mentioned, and that's, I guess, one of the last points for that. I wanted to mention it because that's really interesting. Many people nowadays talk about machine learning, AI, yada, yada. How do the attackers cope with all of the photos? No, they don't have a backend with AIs, upload all the photos and identify what's interesting. They do it exactly on the phone, because when you take a photo on the iPhone already itself tries to identify what is this photo about. So they check, it's a nice photo at the beach. There is some text in, they extract the text. They see, there is sand and water and coconut and yada yada, and they store all of this meta text. Same for a cat, for example. It's an animal, it's a cat, outdoor, yada yada. It's an adult cat, so it's pretty precise. And they exactly access this meta information from the photos and dig out only the photos which are relevant for them, which has interesting text extracted, for example, or certain tags which they're after. Which is kind of smart to use the already available information out of AI on the iPhone for the purpose of this malware. It's interesting. Like, who would think about that? I guess I'm quite bad with timing, so let's quickly jump to the conclusions. I really, honestly recommend everybody here to store network logs. Not only in the company, also at your home. Who's doing that? Not enough. Congrats to everybody who's doing that. To the rest of you, do it. Really, do it. And of course, that's also why I put this with the photos in. And machine learning AI doesn't always necessarily mean that someone builds an AI or machine learning system in order to do something, either on the defense or offense side. Sometimes you can also simply take advantage of what an AI generated, like in this example. So who knows what will be used in future with that? If you have iPhone backups, and I recommend everybody of you who has an iPhone does it regularly and store it regularly, and also have the password set in order to have like all of the information, you can use it's open source, download it from GitHub, go through these backups and see if you had it or not or whatsoever. But other than that, already store it. Store as much as possible, and then you have the ability to discover interesting things like what we did. That's exactly how you do it. Thanks. I hope I'm good in time. Think so. Thanks all for your attention. If you have any questions, feel free to ask me. Thanks for joining me. Question.
Yeah.
Yeah.
Thank you for the presentation. I have a question. Do you have an example of what type of tags or text they were looking for in the images?
Not really, because it's live communication.
Okay.
You don't know.
Thank you.
Question over here.
Thank you for the presentation. I had a question. So as you mentioned, the attack is quite sophisticated. Was Kaspersky able to determine the reach of such an attack? That is, how many people were affected or not?
Okay, the problem with that is, again, this point of you cannot install software on iPhone. So you cannot have an endpoint protection whatsoever. Without that, you don't have any insights into that. We only know about the victims who reported it to us, that they were victims, or the ones who we spotted in our own company. But at the moment, till it's unknown how many people really in the world were affected with that. We know there are some in Moscow somewhere. There were some in Europe. Where else and how many, it's unknown. Sadly, because we cannot do it. Like, we cannot even try to get this information because it's simply not there.
Thanks.
I'm sorry. I would also be super interested, honestly.
Thanks for the talk. Just a question. Do you know, so seeing that you have CVEs for that, I'm assuming Apple either has patched it or will patch it. Do you know if it's persistent, and those people that were affected, do they still have it? They actively have to remove it, or does Apple remove it for them?
The good thing is, in this case, if you do a reboot, it's gone. You get reinfected. But due to the fact that Apple patched the vulnerabilities, this same method won't work again. If they find other ways, of course, then again, it's the same game. But yeah, that stuff luckily is in memory. Which is also smart from that perspective, because you cannot, you don't need persistence when you have this attack chain, because you can reinfect like this.
Any other questions?
Any other? Oh, there's one in the middle.
Yeah.
Sorry.
What's your experience working with like a big vendor like Apple and so? Because I imagine that while you are doing your technical analysis, any help from the company would also substantially help, no, in the analysis. For example, when you were saying that you cannot say how many victims, probably if you can correlate like the messages sent by those addresses, then you would know the victims or the potential victims, right? So how much interaction you had with Apple?
Basically, we reported all of the exploits beforehand, before we published it, like the usual ethical vulnerability publication process. They fix it, that's okay. But that data, I don't even know, like, even if they would store it, they would probably not hand it out. And I'm also not sure if they really store all of this information for that period of time. Like, as I said, we have traces that code is old at least more than 10 years. So if you just say, let's say 5 years, okay? 5 years active operation, just as an example, yeah, not that it's true or not. Do they really store for 5 years who sent from which ID to which ID which message? I don't think so. Why would they? So, yeah, you don't get this information. But, I mean, in general, honestly, like putting it more on a general side, in many cases, if you talk nicely with people, people talk nicely to you. It always depends on how you approach certain companies. I've seen other cases where the companies were not that happy because other people were not so nicely communicating. So first of all, it's always about how you communicate with the people and finding the right people to talk to. And then usually it's not a problem. But don't expect that you get, for example, this kind of more sensitive information back from companies, because also based on regulation, you simply cannot get this data from, even if it's there. So I would not blame anyone in this case, also not Apple, if they would theoretically have it, which I don't think they have, to not release it because it's not possible in many cases from a legal perspective. But working with them in order to get this fixed, they did it, which is good. So they're actively interested in making their product secure. And if there's any exploit, they go for it. Like every company should do, right? No more questions? Very good. Find me later. Find me on Twitter. Find me on any social network. Talk to me. I'm happy about. Have a nice day and other great talks, and hope you learned something.
Thank you, Marco.